Water. Water comes in many forms. Groundwater, surface water, drinking water, wastewater, stormwater, or dual use and reuse. Some may need greater treatment than others, depending where it is discharged or on how it is used. In the end, however, it is all water. This program is meant to be a general wastewater overview that will examine secondary treatment. Understand that no two treatment plants are identical, and that while there are variations between treatment methodologies and plant designs, usually because of the region or climate, the science and concepts remain the same. It was not until the late 19th century that the beginnings of sewerage, infrastructure designed to convey sewage, was implemented in North America. Outbreaks of cholera, typhoid, and other waterborne diseases during these early years challenged scientists. The research of Louis Pasteur and Robert Koch provided the scientific proof for germ theory and the presence of waterborne disease. The knowledge impact of harmful organisms contained in sewage illuminated how inadequate disposal could harm human health. Cities rallied to build collection systems to carry waste away, usually to the closest waterway. Policymakers and city engineers of the time believed that the flowing waters would purify the sewage. In 1899, the Rivers and Harbor Acts was passed, but it would be years before meaningful follow-up legislation would arrive. As late as 1905, an astounding 95% of urban development used waterways for sewage disposal. Controversy started over water quality and how to best protect drinking water supplies. The debate centered on whether wastewater treatment or water treatment best served public health. And few cities could then afford to build both water and wastewater treatment facilities. In the early 20th century, public opinion, local legislation, and affordable wastewater technology shifted in favor of centralized wastewater treatment. Probably the most influential development supporting wastewater treatment was the demonstration of the cost-effective use of the activated sludge process to treat large volumes of wastewater. Through the 1940s and 50s, cities struggled with urban industrialization, suburbanization, and unmitigated post-war expansion. The Water Pollution Control Act of 1948 provided needed enforcement and financial assistance to build collection and treatment facilities. This act was extended in 1952 and became permanent legislation in 1956. In 1965, amendments to the Water Pollution Control Act strongly addressed the issue of protecting water quality. This is the first shift in the fundamental goal of wastewater treatment from public health to an added goal of water quality. Despite these efforts, U.S. waters were deteriorating, and in 1972 the federal government took a significant stance on water pollution and passed the Clean Water Act. The Clean Water Act was instrumental because it was a funded mandate distributing federal funds to states and municipalities. The Clean Water Act established the basic structure for regulating pollutants discharged into the waters of the United States. This is known as the National Pollutant Discharge Elimination System, or NPDES. The NPDES permit program controls water pollution by regulating point sources, including wastewater treatment plants, which discharge pollutants into U.S. waters. Every wastewater treatment plant must obtain an NPDES discharge permit that establishes plant effluent water quality requirements, which ultimately define treatment strategies. Region, climate, finances, available footprint, and receiving water quality are a few considerations that can shape wastewater treatment decisions. The methodology for treating wastewater is well established and fairly unified. The method of treatment in which the application of physical forces predominate, such as mechanical separation using bar screens, is called a unit operation. The method of treatment in which the removal of contaminants is brought about by chemical or biological reactions, such as disinfection, is termed a unit process. Together, they provide the various levels of treatment known as preliminary, primary, secondary, and advanced or tertiary treatment. In preliminary treatment, rags, sticks, floatables, and grease are mechanically separated from the flow. These objects can cause maintenance and/or operational problems downstream. In primary treatment, settleable solids and a portion of organic matter they exert are typically removed through sedimentation. Secondary treatment provides removal of biodegradable organic matter and suspended solids. In advanced treatment, additional combinations of unit operations and processes are used to remove residual suspended solids and other constituents that are not reduced significantly by conventional secondary treatment. This program focuses on the secondary or biological unit processes which are designed to remove the unseen pollutants. Wastewater flowing out of the primary process still contains both floatable and dissolved solids. In nature, this organic mix would be considered a buffet for microorganisms and bacteria. The theory for the secondary treatment process is to create a highly controlled environment created specifically for these microorganisms to work as fast and efficiently as possible in breaking down the organic materials. In AWWA's Wastewater Microbiology, information is available to help understand the different types of bacteria, protozoa, and metazoa, including how to classify them and their roles in wastewater treatment. Bacteria are the most numerous and important microorganism since they work to remove organic materials from the wastewater and help form floc. Bacteria make up about 95% of microorganisms in activated sludge, followed by protozoa with about 3%. Protozoa are grouped as amoebas, flagellates, and ciliates. Protozoa play a critical role in the treatment process by removing and digesting free-swimming dispersed bacteria and other suspended particles. This improves the clarity of the wastewater effluent. Lastly, are metazoa, which are zoological multicellular organisms that include all animals except protozoa. This means all creatures from elephants down to rotifers. Rotifers are more complex organisms than protozoa. Rotifers clarify the effluent by removing leftover bacteria, algae, and smaller protozoa and help create floc. Wastewater operators control oxygen levels, temperature, and detention time to support these microorganisms as they consume dissolved matter, converting it to suspended solids, which can be settled out in a secondary sedimentation basin. One of the most common forms of the secondary treatment is the activated sludge process or the suspended growth activated sludge process. This usually is comprised of an aeration basin and the solid separation equipment, or a gravity sedimentation basin called the secondary clarifier. In this process, the incoming wastewater and microorganisms are suspended and mixed in a large basin and aerated for anywhere from a few hours to several days. Operating an activated sludge process is a complicated, continuous process because wastewater flows through the plant 24/7, and there needs to be enough hungry microorganisms to keep the process going. The activate sludge, or mixed liquor suspended solids, flows from the aerated basin to a sedimentation basin or clarifier to allow the suspended solids to settle, creating a sludge blanket. A portion of this sludge blanket is piped to the solids processing area for further treatment and is called waste-activated sludge. There are many variations on the active sludge process. Each variation is designed to address a specific issue or problem. Some modifications are characterized by differences in mixing and flow patterns in the aeration basin and in the manner in which the microorganisms are mixed with the incoming wastewater. Fixed growth activated sludge systems are designed to keep wastewater in contact with microbial growths attached to surfaces of supporting media. Types of fixed growth systems include trickling filters, where wastewater is distributed over a bed of media, a biological tower where wastewater is distributed over 14 to 20 feet of synthetic media, or a rotating biological contactor, where a series of circular plates on a common shaft are slowly rotated while partially submerged in wastewater. Although the physical structures differ, the biological process is the same in all of these fixed growth systems. Wastewater is distributed over the fixed media, producing a biological slime that coats the surface. These biological slimes include bacteria, protozoa, fungi, and other living organisms that coat the surface of the fixed growth systems and feed on organic wastes. Organisms attached to the media in the upper layer grow quickly, feeding on the food supply. One of the most commonly used fixed growth systems is a trickling filter. The filter serves a dual purpose of filtering the wastewater and supporting biological growth that feed on the waste materials. Physically, the trickling filter looks like a circular basin filled with natural rock or slag or synthetic materials that are usually 2 to 5 inches in diameter, since very small filter materials tend to slow and impede the flow of water and air. Positioned above the bed is a lateral or rotary, moving wastewater distributing arm. This arm distributes the wastewater as evenly as possible over the trickling bed. As the wastewater trickles downward, the organic content decreases to the point where microorganisms toward the bottom layer are starving. Biological filtration is commonly referred to as aerobic treatment, but it is in fact a facultative system incorporating both aerobic and anaerobic activity. Excess microbial growth sloughs off the media and is removed in the secondary clarifier. Unseen below the filter medium are the underdrains that connect the returning liquids to the effluent channels. Biological oxygen demand must be taken into account since the agents of change are biological in nature. The BOD load on a trickling filter is calculated by using the BOD in the primary effluent applied to the filter, not including the recirculated flow. Here are some of the basics an operator needs to know about biological oxygen demand hydraulic loading. BOD loading equals the settled wastewater, BOD, divided by the volume of the filter media, where the BOD loading equals the pounds of BOD applied per 1,000 cubic foot per day. Settled BOD equals the wastewater BOD remaining after primary sedimentation in pounds per day. The volume of media equals the volume of the stone in the filters in thousands of cubic feet or cubic meters as the case may be. Hydraulic loading is the amount of liquid applied to the filter surface, including both untreated wastewater and recirculated flow. Surface loading is commonly expressed in units of millions of gallons per acre per day or gallons per minute per cubic feet. This can also be expressed in cubic meters per square meter per day. Hydraulic loading is represented as the following equation, where Q equals the wastewater flow, QR equals the recirculation flow, and A equals the surface area of the filters in acres. Recirculated ratio is computed as follows. QR equals the recirculation flow, and Q equals the wastewater flow. Membrane bioreactors, or MBRs, is another activated sludge process which draws wastewater through a membrane filter, leaving the solids in the tank and allowing the clean water to flow through. The membranes replace the function of both clarification and filtration. Some communities use aerated basins or lagoons for secondary treatment. These stabilization ponds use algae growth, sunlight, and oxygen to break down the organics in wastewater. Since this reaction is relatively slow, these ponds are typically aerated to speed up the process. These installations are typical in small systems. Tertiary treatment is used to further improve the water quality prior to discharge. These systems may be designed to remove specific substances like metals, but are typically designed to further remove solids and nutrients. Large quantities of nutrients harm aquatic environments by stimulating algae growth and other vegetation that deplete the much-needed dissolved oxygen required by fish and other aquatic life. The two primary nutrients removed in tertiary treatment are phosphorus and nitrogen. Phosphorus can be removed physically with membrane filtration. chemically through precipitation using aluminum, calcium, or iron-based coagulants. Phosphorus can also be removed through biological phosphorus removal. Although chemical precipitation is more predominant, BPR is gaining popularity because it can remove phosphorus to lower levels at relatively manageable costs. En route to the treatment plant, much of the nitrogen contained in the raw wastewater gets converted from organic nitrogen to ammonia. In the plant, this ammonia is then converted to nitrate using a process known as nitrification. Nitrification employs special bacteria to convert ammonia to nitrate compounds, which are a less harmful form of nitrogen. On the discharge side, some receiving waters are so sensitive to nitrogen compounds that the remaining nitrogen must be removed through a process called denitrification. Denitrification further converts the nitrogen in nitrates to nitrogen gas, which is vented to the atmosphere. Up to this point in the process, the unseen materials have been being digested and becoming suspended solids that will settle and can then be removed. However, sometimes it is necessary to remove additional solids through traditional filtration or multimedia filters. In this process, wastewater is passed through granular material, such as sand and coal, to achieve lower suspended solids. Eventually, these filters will become clogged with solids, and backwashing or reversing the wastewater flow is necessary. The removed solids are then sent back through the treatment plant for further processing. In the instance where a very high-quality effluent is desired or required, membrane filters can be used in place of granular filters. The purpose of disinfection is the destruction or inactivation of pathogenic bacteria and/or viruses before the water is discharged into the environment. Traditionally, chlorine has been widely used as a disinfectant because of its ability to destroy target organisms. Chlorine can be applied in many forms, including chlorine gas and hypochlorite solutions. The required degree of disinfection is achieved by varying the chemical dose and the contact time. Chlorine dosage will vary based on chlorine demand, the wastewater characteristics, and discharge requirements. Alternative treatment methods are gaining popularity as treatment needs, security considerations, and affordability converge. Sodium hypochlorite solutions, ozone disinfection, and ultraviolet technologies are becoming more widespread. Following disinfection, chlorine residuals can exist for many hours. To meet receiving water quality objectives, chlorinated wastewater effluent is often dechlorinated before being discharged into the environment. Dechlorination is the process of removing the free and combined chlorine residuals to reduce residual toxicity after chlorination and before discharge. Dechlorination can be accomplished by the addition of sulfur dioxide or sodium bisulfite or sodium metabisulfite. Activated carbon can also be used. The total chlorine residual is reduced to a level that is not toxic to aquatic life. Aeration of the dechlorinated water is usually low-tech via a ladder step or a constructed waterfall arrangement that adds needed dissolved oxygen to support the aquatic environment. As our ability to scientifically test and examine contaminants expands, new pollutants including heavy metals and synthetic chemical compounds will be discovered and eventually need to be treated or removed. The solution may be partially internal to wastewater treatment and/or external, requiring preliminary treatment at the industrial site. Looking forward, there is much to be considered when it comes to solutions for total water treatment. To return more usable water to receiving lakes and streams, new methods for removing pollutants are being developed. Advanced waste treatment techniques in use or under development range from biological treatment capable of removing nitrogen and phosphorus to physical-chemical separation techniques such as filtration, carbon absorption, distillation, and reverse osmosis. These wastewater treatment processes, alone or in combination, can achieve almost any degree of pollution control desired. Waste effluents purified by such treatment can be used for industrial, agricultural, or recreational purposes, or even drinking water supplies. Since the beginning of urbanization, the organic precursor to civilization, health has been predicated on safe drinking water and adequate wastewater disposal. The rise of megacities is directly attributable to the important work wastewater operators and engineers do every day, protecting public health through robust wastewater collection and treatment systems. The following section is a review of math techniques that can be beneficial to wastewater treatment operators when working with trickling filters. Here's the question. What is the organic loading rate in pounds BOD5 per day per 1,000 feet cubed for a trickling filter that is 151 feet in diameter and 5.10 feet deep if the primary effluent flow is 1,220 gallons per minute and the BOD5 is 207 milligrams per liter? First, determine the volume of the trickling filter in feet using this equation. Volume in feet cubed equals 0.785 times the diameter squared times the depth of the tank in feet. Plugging in the numbers, we get volume in feet cubed equals 0.785 times 151 feet squared times 5.1 feet, which equals 91,283.8 feet cubed. Next, factor out 1,000 feet cubed from the volume, or 91.2838 times 1,000 feet cubed. Next, convert the gallons per minute to million gallons daily. Number of million gallons daily equals 1,220 gallons per minute times 1,404 minutes in a day, divided by 1 million millimeters, which will equal 1.7568 million gallons daily. Next, determine the pounds of BOD5 per day per 1,000 feet cubed using a modified version of the pounds equation. Organic loading rate in pounds of BOD5 daily per 1,000 feet cubed equals BOD5 in milligrams per liter times the flow in millions gallons daily times 8.34 pounds per gallon divided by the volume of the trickling filter in feet cubed divided by 1,000 feet cubed. The organic loading rate in pounds of BOD5 daily per 1,000 feet cubed equals 207 milligrams per liter of BOD5 times 1.7568 million gallons daily times 8.34 pounds per gallon divided by 91.2838 times 1,000 feet cubed. So the organic loading rate in pounds of BOD5 daily per 1,000 feet cubed equals 33.225, rounded to 33.2 pounds of BOD5 daily per 1,000 feet cubed. Communities with good wastewater systems are communities that can continue to expand and grow by protecting public health through robust wastewater collection and treatment systems.